In this video, we'll talk about a bunch of formulas we have for computing antiderivatives. The point here is the really only way we can do this is by reversing derivative rules that we already know into rules for doing antiderivatives. In general, we'll see this is really the only tactic we have for doing this, which is what makes it a lot more difficult to find antiderivatives than just derivatives like we had before. So let's start with power rules. So the power rule for differentiation said that if I take the derivative of x to the n, I would get nx to the n minus 1. And now I want to work this backwards to know what it means to take the antiderivative of some power of x. Right at the outset, if I divide both sides by n, this tells me that the derivative of x to the n over n is x to the n minus 1. This works for n not being 0 because I can't divide by 0 otherwise. So what does this tell me? Well, this tells me that the antiderivative of x to the n minus 1 is x to the n over n, for n not 0, or, shifting everything up by 1, we have that the antiderivative of x to the m is x to the m plus 1 over m plus 1, for m not equal to minus 1. That's our first rule that we can use to find antiderivatives of functions. So for instance, the antiderivative of x squared is x cubed over 3, replacing m by 2, what we saw in the previous video. There's one other rule related to this, and that's the logarithm rule. Right? We know that if I differentiate the log of x, I get 1 over x, which, turning that around, tells me that the antiderivative of 1 over x is log of x. And in particular, I need log of absolute value of x because log is only defined for positive values, but 1 over x is defined for all of them. This also fills in the gap that we had before. Right? The power rule had x to the m going to x to the m plus 1 over m plus 1 for m not equal to minus 1. This here is the m equals minus 1 case. It's 1 over x. And so that will give us the logarithm when we take the antiderivative. We can keep going, moving on to trigonometric functions. Each of our different rules for trigonometric functions gives us an antiderivative rule flipping it around. So the fact that the derivative of sine of x is cosine of x tells us that the antiderivative of cosine of x is sine of x. And for all of these, if you wanted general antiderivatives, you just add the plus c on the end to be the arbitrary constant. And we get the same exact setup here for all of our different trig rules. There's our remaining 5 derivative rules, and these all turn into antidifferentiation rules, flipping them around. And so then we get that the antiderivative of minus sine of x is cosine of x. For secant squared, we get tangent. Secant tangent gives us secant. Antiderivative of minus cosecant squared is cotangent, and minus cosecant cotangent is cosecant x by inverting all of these rules. Next, we have exponential rules. Exponential rules, we know that if I differentiate e to the x, I get e to the x, which again tells me that the antiderivative of e to the x is still e to the x. Now we can go a little farther with this one, involving the chain rule a little bit. So we know how to differentiate e to the 2x. Right, this gives me 2e to the 2x. And so we can then divide by 2 on both sides to give me that the derivative of e to the 2x over 2 is e to the 2x. Now this 2 here isn't really special, so we could see that the derivative of e to the ax over a is e to the ax for any a that's not 0. Therefore, I get that the antiderivative of e to the ax is e to the ax over a, and this simplifies to our previous case when a is 1. Finally, we have our inverse trig formulas. We know how to find the derivatives of inverse trig functions, and this gives us 3 additional antiderivative formulas. Namely that the antiderivative of 1 over root 1 minus x squared is inverse sine. The antiderivative of 1 over 1 plus x squared is inverse tangent. And then the last one, the antiderivative of 1 over x root x squared minus 1 is inverse secant. Again, just by flipping around the direction of all these formulas. For this example, I want to find the general antiderivative of this function, 2x cubed minus 4x squared plus 2x plus sine x plus e to the x plus inverse tangent of x. And basically the main thing you want to look at here is just do every term one by one, see what you get, and then make sure, because you want the general antiderivative, you want to have an arbitrary plus c on the end. So I can start from the left. 2x cubed would give me the power rule. So I have an x cubed, so it's going to go to the x to the fourth over 4. So it'll be a 2 times x to the fourth over 4. The 4x squared is also power rule, 4 times an x cubed over 3. The 2x is also a power rule, 2 times x squared over 2. Sine of x is one of our trig rules. We know the antiderivative of sine is going to be minus cosine. E to the x is the exponential rule. So this is just e to the x. And inverse tangent is our inverse trig formula. This is going to be 1 over 1 plus x squared. So it means that my full antiderivative is going to be just adding all of these up and then putting a plus c on the end. So I will get a 1 over 2x to the fourth, simplifying the first term, minus, carrying down from above, 4/3 x cubed plus an x squared minus a cosine of x plus e to the x plus 1 over 1 plus x squared, and then plus an arbitrary constant c. You can apply all these rules in order, make sure you tack a c on the end because you're arbitrary constant, and that will give you how to find the general antiderivative for more complicated functions, so long as it's only made up of adding and subtracting individual bits that you already know how to find the antiderivative of. Finding antiderivative is hard because you only really have these base formulas to build from, but if the setup works for it, you can use that to find the antiderivative for these functions as well.